The ocean swallowed most of the evidence. When the Ice Age ended and glaciers melted, sea levels rose more than 120 meters. The ancient coastlines where the first Americans walked, their campsites, their harbors, the very beaches where they stepped ashore, all of it vanished beneath hundreds of feet of seawater. For decades, archaeologists searched for proof that people traveled down the Pacific coast 13,000 years ago, but the rising ocean had erased the trail, except in one place. On a remote island off the coast of British Columbia, archaeologist Daryl Fedje was digging through wet sand at low tide when his trowel hit something different. About 60 centimeters below the surface, the modern beach sediment gave way to an ancient soil layer, a paleosol, buried and forgotten for thousands of years. Pressed into that gray clay was a depression, a pattern. It looked like a footprint, maybe from a bear, maybe from a person, or maybe just an old tree root that had rotted away long ago. He called his colleague Duncan McLaren over. They stared down into the dark, waterlogged pit as rain hammered the beach and seawater crept closer with the incoming tide. Neither man was certain what they were seeing. They took a photograph and they collected wood samples trapped in the impression. Then they filled the hole back in, covered it with plastic sheeting, and left. 6 months later, the radiocarbon results came back. The wood from inside that footprint was 13,200 years old. The following season, they returned with a larger team. This time, they opened a 2-meter by 2-meter excavation. They dug through sand and gravel, racing against the tide, water pooling in the low spots, mud everywhere. Then Fedje reached the gray clay layer where he had spotted that strange impression a year earlier. When they carefully brushed away the black sand that had buried the ancient shore, they found 29 human footprints, 2 adults, a child, bare feet pressed into soft clay, preserved beneath the beach for more than 600 generations. The discovery raises a question more important than their age. Most of the Pacific coastline from that time is underwater now, drowned, inaccessible. Archaeological sites in California, Oregon, Washington, all of them lost beneath the waves. Calvert Island should have suffered the same fate. Its ancient shorelines should have been swallowed by the rising sea or pushed high into the mountains by the rebounding land. So how are these footprints still here? How did this one island preserve what the ocean destroyed everywhere else? The answer reveals why archaeologists can now prove the Kelp Highway was real, and why British Columbia's coast holds secrets that the rest of North America lost forever. Before we get into how these prints survived when almost nothing else did, a quick question. Where in the world are you watching from, and what time is it there? Drop a comment with your answer. I love seeing how far lost evidence reaches across the globe. And if you are blown away that 13,000-year-old footprints prove humans walked a coastal route that should not even exist anymore, hit like. It brings these stories to people who actually want to know how the first Americans really arrived. To understand why Calvert Island is extraordinary, you first need to understand the forces that destroyed everything else. 20,000 years ago, at the peak of the last glacial maximum, ice sheets more than a mile thick covered most of Canada. In some places, the ice was 2 miles thick, 3 kilometers of frozen water pressing down on bedrock. The sheer weight of all that ice, trillions upon trillions of tons, pressed the Earth's crust downward. Imagine pushing your thumb into soft clay. The crust beneath the ice sank hundreds of meters in some locations. This was not a subtle effect. The land around Hudson Bay was pushed down so far that even today, more than 10,000 years after the ice melted, it is still rising. The crust there is rebounding upward several hundred meters. In another few thousand years, Hudson Bay will disappear entirely as the seafloor rises above sea level. At the same time that all this ice was pressing down, so much water was locked in those glaciers that global sea levels dropped 130 meters, 400 feet. Coastlines extended far beyond where they are today. Land that is now deep ocean, 100 meters underwater, was dry ground, walked by humans and animals. Then the Ice Age ended. Around 17,000 years ago, the climate warmed. The glaciers began to melt, two massive forces started working against each other in a battle that would reshape the entire Pacific coast. Eustatic sea level rise. The global increase in ocean volume from all that melting ice. Water released from glaciers flooded back into the oceans, raising sea levels everywhere. The lowered coastlines began to drown, but at the same time, isostatic rebound started happening. The slow upward bounce of the Earth's crust, freed from the crushing weight of ice. As the glaciers melted and their weight disappeared, the land began pushing back up, rising, recovering from the depression. Which force won, rising sea or rising land, depended entirely on where you were standing. Around Hudson Bay, in the center of the Laurentide ice sheet, where the ice had been thickest, the land was pushed down so far that isostatic rebound has dominated. The land there is still rising today, faster than sea level. The crust is slowly bouncing back. Eventually, the entire bay will become dry land again. On Haida Gwaii, the islands off the northern coast of British Columbia, the opposite happened. These islands were not covered by the main ice sheet. Instead, they sat on what geologists call the forebulge, the peripheral zone around the ice sheet. Imagine standing on a trampoline. When someone steps in the middle, the edges push upward. The same thing happened with the Earth's crust. The weight of the ice in the interior pushed the edges up. When the ice melted and the forebulge collapsed, Haida Gwaii fell. The land there has dropped 150 meters since the Ice Age. Ancient shorelines that were once above sea level are now drowned deep beneath the waves. On southern Vancouver Island, yet another pattern emerged. The land there was depressed by ice during the glacial maximum, then rebounded 100 to 200 meters as the ice melted. Streams that once flowed gently into the ocean now plunge over cliffs as 5-meter waterfalls. The land rose faster than the sea. The ancient shorelines are now high in the mountains, far above the reach of modern archaeologists. This is the chaos that coastal archaeologists face. The same stretch of coast, separated by just a few hundred kilometers, experienced wildly different vertical movements. What was a beach during the Ice Age could now be 200 meters underwater, or 200 meters in the air, or anywhere in between. Predicting where ancient shorelines ended up requires detailed geological work, sediment cores, diatom analysis, radiocarbon dating, mapping how the crust responded to the ice loading and unloading. Except at Calvert Island, Duncan McLaren and Daryl Fedje, both archaeologists with the Hakai Institute and the University of Victoria, spent years studying this problem. McLaren had done his doctoral research on the Dundas Islands, just south of the Alaska Panhandle, mapping ancient sea level changes there. Fedje had spent 3 decades as a Parks Canada archaeologist, directing major excavations on Haida Gwaii and mapping how sea level had changed across that archipelago. They knew that understanding sea level history was the key to finding Ice Age sites on the coast. Find the ancient shorelines and you find the sites. But the Pacific coast presented a puzzle with 100 different solutions. Each island, each bay, each inlet experienced its own unique pattern of sea level change, driven by the complex interplay between eustatic and isostatic forces. The researchers needed to find a zone where those forces had balanced perfectly, a place where the land had remained stable while the ice melted. A geological hinge. In 2014, McLaren, Fedje, and their team published a detailed study of sea level history on the central coast of British Columbia. Using sediment cores taken from ponds and lagoons, analyzing deposits of single-celled algae called diatoms, and radiocarbon dating organic materials, they reconstructed how the ocean had risen and the land had moved over the past 15,000 years. They discovered that Calvert Island sat exactly on the boundary between two opposing forces. To the south, Vancouver Island was rebounding upward, freed from the ice that had depressed it. To the north, Haida Gwaii was subsiding, collapsing as the forebulge disappeared. But Calvert Island, positioned between the two, experienced minimal vertical movement. The sea level there had changed, yes. It had been 2 to 3 meters lower during the late Pleistocene. But unlike everywhere else on the coast, that ancient shoreline was still accessible. It was not 200 meters underwater like Haida Gwaii. It was not 200 meters in the air like southern Vancouver Island. It was right there, in the intertidal zone, buried under 60 centimeters of modern beach sediment. This was extraordinary. A narrow window of time and space where the geological chaos that destroyed the rest of the coastal archaeological record had been paused. The researchers knew exactly where to look. They began surveying beaches on Calvert Island, searching for places where the modern intertidal zone corresponded to the ancient shoreline. They dug test pits, narrow holes punched through the beach sand, probing for buried paleosols. And that is when Daryl Fedje's trowel hit the gray clay and found the first impression. The preservation of the footprints required a very specific sequence of events. First, the people had to walk across wet clay, not dry sand, which would not hold a print, not soft mud, which would slump and collapse. Clay at just the right consistency, wet enough to deform under pressure, stiff enough to retain the shape. Second, the prints had to be buried quickly, within hours or days at most. Otherwise, rain would erode them, wind would fill them with debris, animals would trample them, the tide would wash them away. What buried the footprints at Calvert Island was black sand. Fine-grained sediment washed over the prints from the nearby intertidal zone, likely during a storm event. The sand filled the depressions completely, protecting them from erosion. Then more sediment accumulated on top, layer after layer, the beach building upward over thousands of years. The black sand acted as a seal. It prevented the clay from drying and cracking. It blocked oxygen from reaching the organic materials trapped in the prints, preserving the wood fragments that would later provide radiocarbon dates. And most importantly, it held the shape. Even as the beach shifted and changed over 13,000 years, the prints remained locked in place, frozen in time. This kind of preservation is rare. Human footprints from the Pleistocene are extraordinarily scarce worldwide. Most vanish within hours. A few survive in volcanic ash, sealed by eruptions. Others are found in caves, protected from weather. But footprints on an open beach, exposed to tides and storms, lasting for thousands of years, are almost unheard of, which is why the geological stability of Calvert Island matters so much. It is not just that the ancient shoreline remained accessible, it is that the shoreline remained stable enough for delicate features, like footprints, to survive. On Haida Gwaii, even if footprints had been preserved initially, they would now be 150 meters underwater, crushed by water pressure, scoured by ocean currents, inaccessible to excavation. On southern Vancouver Island, they would be high in the mountains, exposed to erosion, weathering, root growth, freeze-thaw cycles destroyed long ago. But on Calvert Island, the hinge held, the land stayed put, the prints stayed buried, and when archaeologists finally arrived with the knowledge to find them, they were still there, waiting. The discovery transforms our understanding of the late Pleistocene Pacific coast. It provides direct, physical evidence that people were living on the shorelines of British Columbia 13,000 years ago. Not just passing through, but living there, walking barefoot on beaches, building fires, making tools, raising children. The environment they inhabited was radically different from today. Sea level was lower, exposing more land. The climate was colder. The landscape was in flux, emerging from the grip of the Ice Age. On northern Vancouver Island and nearby Haida Gwaii, recent studies by Bryn Latham, Daryl Fedje, and others, published in Quaternary Science Reviews in 2024, show that some areas became ice-free as early as 18,200 years ago. The retreat of the Cordilleran ice sheet was not uniform. Some coastal zones were deglaciated thousands of years before others, creating refugia where plants, animals, and humans could survive even during the coldest periods. The vegetation was different, too. Instead of the dense rainforests that blanket the coast today, the late Pleistocene landscape was more open, with pine forests and stands of spruce, hemlock, and fir at lower elevations. Grasslands and shrublands appeared in other areas. The forests we think of as primordial and ancient are actually recent arrivals, established only in the last 10,000 years as the climate warmed. The animal life was equally different. Faunal remains preserved in karst caves on Haida Gwaii and northern Vancouver Island show the landscape was inhabited by cold-adapted animals that later became extinct or extirpated as the climate warmed. Brown bears, deer, sea mammals like seals and sea lions, and offshore extensive kelp forests. Even during the Ice Age, even at the coldest periods, kelp forests thrived along the Pacific coast from Alaska to California. Kelp needs cold, nutrient-rich water and rocky substrate to anchor to. In return, it creates one of the most productive ecosystems on Earth. Kelp forests are three-dimensional habitats, biodiversity hotspots. They sport fish, shellfish, sea urchins, sea otters, seals, sea lions, and seabirds. Everything a maritime culture would need to survive. Fish to eat, shellfish to gather, sea mammals to hunt, birds and their eggs, and seaweed itself edible and nutritious. For people with boats, the Pacific coast during the Ice Age was not a barrier. It was a highway, a Kelp Highway. The footprints at Calvert Island prove people were living on the coast of British Columbia 13,000 years ago. At the same time, the Clovis culture was emerging in the interior of North America. The stone tools found with the footprints are not Clovis points. They're different, a distinct lithic tradition. This supports what archaeologists call the coastal migration hypothesis, the idea that the first people in the Americas did not walk through an ice-free corridor between glaciers in Canada. They traveled by boat, following the Pacific coastline south from Beringia, the now submerged landmass that once connected Siberia and Alaska. The ice-free corridor theory, the dominant explanation for most of the 20th century, has a critical problem. Recent studies of the corridor's opening show it did not become passable until about 12,000 years ago. And even when it opened, biological evidence suggests it was a barren wasteland for centuries, with no plants, no animals, nothing to eat. It would have been impassable for humans attempting a multi-generational journey south. The footprints at Calvert Island predate the opening of that corridor by more than 1,000 years. People were already living on the coast of British Columbia while the ice sheets still blocked the interior. The only way they could have arrived was by sea. This is not speculation based on theoretical models. This is physical evidence, human footprints, hearths, stone tools, the remnants of a way of life. And Calvert Island is not the only site proving this. Just south of Calvert, on Triquet Island, McLaren and Fedje's team found a village site dated to at least 14,000 years ago. Stone tools, hearths, layers of shell midden, the accumulated refuse from generations of people eating shellfish and discarding the shells. The site shows continuous or repeated occupation spanning thousands of years. On Haida Gwaii, to the north, archaeologists have found early sites dating back more than 13,000 years. Karst caves there yielded stone tools, animal bones, and even a domestic dog tooth dated to 13,100 years ago. The oldest evidence of domestic dogs in the Americas, these discoveries are not isolated finds. They represent a pattern, a coastal population living, fishing, hunting, and thriving along the British Columbia coast during the late Pleistocene. While the interior of North America was still locked under ice, people were already here on the coast in boats, and we can trace their origins. Humans had been building watercraft and exploiting marine resources for tens of thousands of years before the Americas were peopled. In Japan, shellfish hooks dated to 23,000 years ago show sophisticated coastal fishing technology. In Australia, humans crossed significant stretches of open water to reach and colonize the continent at least 60,000 years ago. The technological capacity existed. The maritime knowledge existed. The boats existed. The idea that the first Americans traveled by sea is not extraordinary. It fits with what we already know about human adaptability, technological ingenuity, and our long-standing relationship with coastal environments. What makes the Calvert Island footprints extraordinary is not that they prove people could travel by boat. It is that they survived to tell us the story. Almost nothing else from that time period did. The rising ocean and the rebounding land destroyed the archaeological record up and down the Pacific coast. Sites in California drowned. Sites in Oregon drowned. Sites in Washington drowned. Sites on southern Vancouver Island lifted high into inaccessible terrain. But here, on this one small island perched on a geological hinge, the ancient shoreline stayed put, stable, accessible, waiting for archaeologists with the knowledge to find it and the patience to dig through 60 centimeters of sand in a waterlogged pit while racing the tide. Duncan McLaren describes the discovery simply. The hair on the back of our necks was standing up. You spend a lot of time looking for bits of chipped rock and animal bones, little fragments, But footprints, those are different. Footprints are direct evidence of people, not their tools, not their trash, not their constructions, the people themselves standing on that beach 13,000 years ago. Daryl Fedje, who spotted that first impression in the dim pit, describes it as pattern recognition. We develop an eye for these patterns, he explains. After walking up and down the beach hundreds of times over multiple field seasons, footprints in the sand get imprinted on you. You learn what to look for, the shape, the depth, the way toes create ridges, the offset heel. But even with that trained eye, even after decades of coastal archaeology, finding these prints was remarkable. The team knew they were looking in the right place because of the sea level studies. They knew the ancient shoreline would be in the intertidal zone, but whether footprints had actually been preserved, whether they would be visible, whether they would survive the excavation, all of that was uncertain. More footprints almost certainly remain buried at the site. The research team has intentionally left much of the area unexcavated. They hope that future scientists with more advanced technology, methods not yet invented, will be able to extract even more information from the preserved layers. DNA analysis, sediment chemistry, techniques we can only imagine now. But the footprints, already visible, already documented, already radiocarbon dated, are enough. They answer the question that has haunted coastal archaeology for decades. Did people use the Pacific coast to enter the Americas? Yes. Can we prove it? Now we can. Because of Calvert Island's unique geology, because of the stable sea level that preserved an ancient shore, because of the hinge between rising land and rising sea. We have footprints, we have hearths, we have tools, we have the remnants of a way of life that everywhere else the ocean destroyed. The footprints are still there, buried beneath the sand at Calvert Island, waiting for the next low tide. Proof that 13,000 years ago, people walked where we walk now. They built fires where we build fires now. They looked out at the same ocean, fished in the same kelp forests, gathered on the same beaches. And against all odds, despite the rising sea and the shifting land, despite 13,000 years of tides and storms and geological chaos, the Earth remembered. The Earth held on to just enough evidence to tell us the truth. The Kelp Highway was real. The first Americans came by sea, and the footprints at Calvert Island prove it. If you enjoyed discovering how unique geology preserved what the ocean destroyed everywhere else, check out the video on screen for more lost evidence.